start. There we go. I did. Hello and welcome back to Calculus 1. We are continuing chapter 4, section 2. We're going to talk about first and the second derivative test. The book has the ridiculous title, What Derivative Tells Us, like we get to talk to it. So the first and the second derivative test will tell us a lot about the function. We are going to discover the intervals where the function is increasing, intervals where the function is decreasing, also concavity. It will help us analyze the function so that we can work with graphs better than before. And then we're going to take everything we learned and put that together and graph functions by hand in 4.3, which is one of the very important sections, especially because you don't have the graphing calculators to do these things on exams. You will need it Calc 2, Calc 3, and then later on, let's say you go out with a friend, a function comes up. Obviously, you know how to graph. All you need is a napkin, and you can always ask servers for pen because they usually carry assortment of pens. True. All right, good. So I just had to validate that one. So I will draw a basic graph of a function. Say looks like this. We've seen something similar in section 3.2. Now, if I am to draw the derivative, this is positive 1, then derivative is 0, and then it's negative 1. We see that any time when the function is increasing, we have a positive value for the derivative. When the function is constant, derivative is 0. And when the function is decreasing, the value of the derivative is negative. Believe it or not, that's all we need to write the procedure for the first derivative test. Number 1, get all critical points and vertical asymptotes. Now you know how to find critical points, right? You will go and do the first derivative equal to 0 and figure out where the function is not differentiable. So all of that good stuff from previous section. And then also you need to know the vertical asymptotes. Now, for number 2, we are going to draw a diagram I'll just set in parentheses partitions. Number 3, test all test points in f prime of x. And now here's the first derivative test. It says if f prime computed at a is larger than 0, then f of x is increasing on that part of the domain. If f prime of a is less than 0, then function f of x is decreasing on that part of the domain. We don't need the 0 here because we know that we are going to see if you plug in 0, you are going to find the points of critical points. So this is your procedure. And let's do the easiest possible example to illustrate this. We all know how y equal x squared looks like. But let's say we don't, right? Let's say you watch the TV for like 17 minutes. That kind of wipes this information out of your head. Yeah, like a soccer game, let's say. So, for 17 minutes, there will be more of an infomercial. Yeah. What was I supposed to do? Oh, yes. We find the derivative, set derivative equal to 0, solve the equation, get a critical point at 0, 0, we all know, right? There are no vertical asymptotes in this case. We are going to partition our domain from negative infinity to positive infinity only at 0 because that's the only critical point we have. And then we choose 2 test points, one in each region, in each partition. And we do the first derivative test by taking the test point and plugging it into derivative. So we see that the function is decreasing on the left of 0 because the first derivative was negative. And then f prime at 1 is 2 times 1, which is positive 2, which is larger than 0, which tells us that f goes this way, which is that. So you see that this correlates very well with your knowledge of x squared graph. You see that there is a minimum at 0 because it falls into 0 and then emerges and rises right to the right of it. So we know there is a minimum here. So you don't get to write whether this is a min or a max until all the way until the end of the problem. So we can immediately see min and max information as soon as you're done with the first derivative test. So first derivative test will give us intervals of increase and decrease of the function because it's changing at that rate. And then at each critical point, you might have min or a max. Could be also inflection point. We'll talk about that. So we use the first derivative test, which means that the test values that I picked in red, -1 and 1, are plugged into the first derivative. So if you are getting now confused what is plugged in the original equation, what's plugged into derivative, well, just use the title of the lecture, first derivative test. You pick the test values, and it's called first derivative test. So test values should be plugged into derivative. If you plug critical point into derivative, you're going to get 0. Not larger, not less. You're going to get 0. So there's no need to plug critical point because it's a single point. But what's guaranteed by math is that if you pick any number from negative infinity to 0 and feed that into the derivative for this particular function, you will always get the decrease. Always get less than 0, and you will always have decrease. Bueno? Good. So, next example is, I was about to say calculus 3, x cubed. So when you have x cubed, f prime of x is 3x squared. Set that equal to 0, x equals 0, and you still get 0, 0. This is the same as the previous problem. No VAs, so we only get to partition again only at 0. Between negative infinity and positive infinity. So first, you ask yourself, what's the domain? And domain in this case is negative infinity to positive infinity. So once you are done with the domain, then you partition. Now, partition means put on the graph all of the critical points and all of the vertical asymptote values. And you will pick the test points in between. Again, we only have two regions here. So pick -1, +1. And let's see what happens as I pick -1 and +1, and I test those in the first derivative. We get that the f is increasing for -1. And that it's increasing after 0 as well. So you see how the graph over there shows me that there is no min and no max at 0, 0. Because in order to have a max, it has to be decrease going into increase, increase going into decrease for max, and decrease going into increase for min. You have both of these increase, which correlates very well with what the cubic function is, if you remember the cubic graph. You see that it's always increasing, right? Cubic graph is always increasing, and calculus confirms that with this exercise. So I will give you one spicier example to work. I worked out 2 easy examples. That's my job, right? And then you work one spicier example. Again, you're taking the derivative, finding critical points, do the partitions. It's just lots of fun. I see. So problem 34 is asking you to do the first derivative test analysis for the function x squared minus 2 ln x. So obviously I do x squared and x cubed, and you guys get ln x. I guess we are going to do this since you guys are all chatting, which means you are all done. So f prime is 2x minus 2 over x. We set that equal to 0 to find critical points. First of all, our domain is 0 to infinity, right? Because you start there with the domain. So now this means 2x is equal to 2 over x. X squared equals to 1. X equals plus minus 1. But then we have to drop the negative because of the domain. And we just have x equals 1 as the only critical point. We also have, so this is critical point, and we also have x equals 0 vertical asymptote. But now partitioning starts at 0 anyway. And here it is at 1. So 0, 1, and going to infinity. So this is how our graph looks like. There is nothing left of 0 because domain is 0 to infinity. And then there is a vertical asymptote. We partition the entire domain using vertical asymptotes and using critical points. The derivative exists at all other points other than the vertical asymptote there, so we already have that. So what are the values that I'm choosing? I'm going to choose 1/2 because that's between 0 and 1, and I'm going to choose maybe 2, the value larger than 1. So now to do the first derivative test, I'll take the first derivative and compute at 1/2, and I'll take the first derivative and compute at 2. That's all I need, because I again only have 2 regions. So first derivative computed at 1/2, so that's 2 times 1/2 minus 2 over 1/2, which is 1 minus 4, which is -3. So we have a decrease, right, for 1/2 there. And then I have number 2, which is 2 times 2 minus 2 divided by 2. That is 4 minus 1, which is +3, and that's the increase. So I know that my critical point over there is the minimum. So now what should I write as the answer here? F of x is decreasing on 0 to 1. F of x is increasing 1 to infinity. So all of these numbers, values inside the intervals are x values. Observe that I never bothered computing the point, the y point for the critical point, because I don't need it. I just need to know where to partition so I can pick test points away from those values. So you can pick anything right over here. You can do e divided by pi if you like pain. Right, that's going to be between 0 and 1. So whatever you choose. I chose 1/2. Years of experience. No?
So you didn't pick a value lower than 0 because it's x squared?
Because domain. ln doesn't go to the left of 0 in a real plane. The second part of this lecture is concavity, which is the second derivative. Second derivative test. You have identical procedure, except this one is done on the second derivative. And instead of getting increase decrease, you are getting concavity now. Now the first order of business is, what is concavity? What does that mean? Well, we say for the shape that looks like this that it's concave up. And a shape that looks like this, concave down. Now that also means that the shapes that look like this are concave up, and the shape that look like this are concave down. Because if you put those two shapes together, you will get these. Now, when I learned this for the first time, professor said, holds the water and then spills the water, right? Concave up holds the water, concave down spills the water. Right? Concave down and concave up. LRVCC. Yeah. You're not messing around. Second derivative test. We are literally doing the same thing as with the first derivative test. All of the steps are the same except you're using second derivative. So, number 1, set second derivative equal to 0. Which gives us inflection points. So you learned so far first derivative equal to 0 is critical points, and second derivative equal to 0 gives you inflection points. The hell is the inflection point? Inflection point is point at which concavity changes. From concave up to concave down, or from concave down to concave up. So that's what we have. Now, the first order of business is obviously you find the second derivative set equal to 0. The points you get are called inflection points. Then get all inflection points and vertical asymptotes. We have the same steps, and then partition. So now, number 3, draw a diagram. So draw a diagram, partition. What do you partition? You partition all inflection points and vertical asymptotes. That's what goes in the mix. And then number 4, finally, is analyze. Now, what is the second derivative test? How that works? You take the second derivative, you get equal to 0. You find the values which you plug back into the second derivative test. So, here's the test. If second derivative computed at A is larger than 0, then function f of x is concave up on the given domain. It could be restricted, right, as well, could be infinite. And if second derivative computed at A is less than 0, what happens then? Concave down. F of x is concave down. On the given domain. So first derivative test, set first derivative equal to 0, get critical points, and then do the testing. Don't forget vertical asymptotes if they are there. And then for second derivative test, what you do is the second derivative equal to 0 to find inflection points and so on. Now is a good time to say that sometimes when you take the first derivative and set it equal to 0, you don't get critical points. Sometimes you also get inflection points. Inflection point is a change in concavity. I already have example for that, so I'm just going to scroll. Oh, I did it on the board. I was going crazy looking for my x cubed graph. So y equals x cubed. We already seen that if you do the first derivative test, first derivative tells you there's no min or max. Awesome. But if you are to take two derivatives in a row, first derivative and second derivative, here's your second derivative, 6x. So now what's happening? We are going to draw the diagram, split that diagram at 0 because we still have y to equal to 0. And we pick two test points, one to the left and one to the right. So the second derivative computed at -1 is going to be 6 times -1, which is something. -6 less than 0, concave down. F double prime of 1 is 6 times 1 equals 6. Concave up, because this one is larger. Now, we don't draw the shapes, we just say concave up, concave down. So concave down and concave up, that's sufficient. And I think that was my example. But note that if you set the first derivative to 0, you're still getting 0. But from here, when you set it equal to 0, oh, I didn't write equal to 0 and then x equals 0. Inflection point. That would be helpful on the first example of the lecture. To write the most important part. So, since I already did example, we did a whole bunch of those examples for first derivative test. I will give you something to enjoy right away. What happened? You should check that out. Huh?
As long as he doesn't answer himself.
I guess it is.
I'm a little bit.
Oh, that's good, because you're never alone.
I always have someone to talk to.
I know. Like other poor people have to bring the mirror and stuff, you know. Like, there are perks to everything, I'm telling you, man. I'm still looking for the threshold of the worst thing I've ever said, but that's... All right, I guess 79 looks awful enough.
That's what I like to hear. He loves that. We're throwing a lot of E's at this.
Yeah, I'll see it. Do we have a problem with it?
I hate you.
What?
Just like, it's like when you see like a hot sandwich, just and it's like complicated.
It's like X and Y are used to T's.
It's like a whole new letter I think. It's like the whole no new friends thing.
Oh, you don't have a
No new friends.
You have how many years ago? More than that. Fun then. Alive. You know the same process. Oh, fuck. Controls won't give me anymore. It's still like
happens when we wait.
So it's like, oh, now.
You're like, I got an answer. And then it's just not the answer.
That's why the exam stressing out piece first, then don't go with it. Then outside twice. So then we don't have. Four plates. So,
Yeah.
So you take the first derivative, then the second derivative.
Yeah.
So let's see these derivatives. We have the first derivative as its product rule, right? So we follow the rules. And then we simplify. I will kick e to the negative x out and have negative x squared plus 2x. I could have kicked an x as well, but I don't want to have a triple product. And I'm not setting that one equal to 0, so I just want to keep it in the form that it's the easiest for me to solve, differentiate. So now again, copy the first, take derivative of the second, plus copy the second, take derivative of the first, which is this, and now simplify. You remember, very, very similar to your exam question, right? So we have e to the minus x together. I have a positive x squared, and then a negative minus 4x, and plus 2. Set it equal to 0. E to the minus x equal to 0, and x squared minus 4x plus 2 equals to 0. This one has no solution, because the exponential function cannot equal to 0. So if all the other calculations went well, this cannot be factored, so we have to use quadratic equation, let's say, quadratic formula. So negative b plus minus b squared minus 4ac divided by 2a, which is 4 plus minus square root of s is 2 root 2. So we get inflection points, the IPs, at 2 plus minus root 2. We have no vertical asymptotes in this case, so our partitioning is done 2 minus root 2, 2 plus root 2, from negative infinity to positive infinity. We are going to have 3 regions here. And then pick test values. Well, look, you are taking away from 2 and you are adding to 2, so 2 must be dead in the middle. And then you can pick out 0 and you can pick out 5, whatever. You are supposed to plug these test values in the second derivative. So second derivative computed at 0, second derivative computed at 2, and the second derivative computed at 5. Now second derivative was e to the x minus 4x plus 2. What happened? That's what I said. Just pay attention. So when we plug 0, we get 1, we get 2. So that's concave up over 0. So from negative infinity to the root, so 2 minus root 2 is going to be concave up. Now we compute the same thing at 2. It's going to be 1 over e squared. And when you compute at 2, you get 4 minus 8 plus 2. So that's negative 2 over e squared. All I care is just negative. So it's concave down. And now we compute at 5. So 1 over e to the 5. And we are plugging in 5. So it's 25 minus 20, 22 over e to the 5. Well, that's still positive. Now the question is, what's larger, 2? Oh, actually, no, wait. I don't. I'm
Because it's x squared is 25 minus
20 plus 1 plus 2
plus 2.
is 22, right?
25 minus 20 is 5.
Ah. 7. Larger than 0, concave up. Yay. There we go. So now, how do you write the answer for these questions? You will say f of x is concave up on negative infinity to 2 minus root 2 union to plus root 2 positive infinity. So you provide x1, x2, x1, x2. You provide 2x values because you are giving the domain, part of the domain. And fx is concave down on 2 minus root 2, 2 plus root 2. That's it. That's all, and I hope you are not disappointed. So both procedures are identical, except you have to be careful. So first derivative gives us critical points, increase, decrease, min, max. Concavity gives us inflection points, concave up, concave down. Now also you can use the second derivative to figure out min and max, because when something is concave up, has a minimum, right? So if you think about your function x squared, which is the easiest one, y equal x squared, and you decide to use concavity to talk about min, max, and everything else. If you look at this, the first derivative f prime is 2x, and the second derivative f double prime is 2. See, 2 is always positive. So the entire thing on the entire domain is concave up. And we know that because the graph looks like that. On the entire is concave up. And you are going to find over here 0, 0 critical point, but because the whole thing is concave up, you know it's a minimum, because concave up has minimum and concave down has a maximum. So you could use the second derivative to claim min and max on every interval as well. So you should think about that as well. Whole bunch of problems on the homework for you to practice. Now I want to also point out that what we're going to do on Monday is this very long section, tedious section 4.3, graphing functions by hands. And you will be calculating about 10 to 13 different things, and then you will use all of those to graph a function by hand. You will be able to take a look at ln of absolute x squared minus 1 and graph it by hand, because you do these calculations, and these are part of it. So there will be calculation on domain and x-intercept, y-intercept, symmetries, asymptotes, all three types, first derivative test, second derivative test, and maybe additional points if you need them, and you will be able to graph a function by hand, any function by hand. You need to know this stuff very well, because we are not learning anything new in 4.3. We are going to go back and say, oh, that's how you find domain. That's how you find x and y intercept. That's how you find. So we are going to take everything we learned so far in mathematics across algebras and pre-calcs and everything, and we are going to put that in a single section and use it to graph function by hand. So that's 4.3. Those problems tend to be lengthy. So what I do is I break, see, for the test, like if one of those problems is like 30 minutes or 40 minutes, it's not good for the test, especially if you go and you mess up on the first derivative and then, right, the problem just explodes. I break on the exam this one long problem into 4 or 5 smaller problems. So there is only a problem on the first derivative test. There is a problem on the second derivative test. There is a problem on min-max. There's a problem on graphing. There's a problem asymptote sprots graphing. So there's a lot of stuff that is happening, and it's much easier. Well, not easier, but it doesn't kill your grade in terms that you are going to mess up somewhere in the beginning, and then 40 minutes of calculations later, you see that something is not working out, and then you see, oh, but there was a -2 that I forgot as a chain rule on the first line, and obviously killed everything else. So that's something that you need to know. The homework will open, obviously, and you guys enjoy chapter 4. 4.3, we might start 4.4 on Monday, or we might just do 4.3 and then do the lab, so you can catch up on labs, because you are behind on labs, right? You handed in lab number 2, and we are, 2 weeks left? So there's lab 3, lab 4, lab 5, exam 3, final exam, and the project, totaling 70% of your grade. 70% is not handed in. So that means if you have 0 so far in this class, you can still pass. All right? If you haven't done anything yet, you can still pass. But you will need 100 on everything right to do. So, guys, just, another 2 weeks of insane grind. 2 weekends of no life. What happened? Yeah. And I will see you all on Monday or sooner. I don't know. All of 4? Homework? I can, free of charge.